Welcome to Pre-Calculus. Today we will investigate evaluating logarithms using the change of base rule. We'll take a look at 3 examples. Our first 2 examples are fairly simple logarithmic expressions. Our first is log base 5 of 25. And with simple expressions like this, we can probably just reason through how the logarithm is written and come up with the evaluation directly. But really, if I have to use a calculator, one thing I need to be aware of is that most calculators, at least traditionally, only had access to log base 10 evaluations. And so when I'm looking at log base 5, there really would have been no way for me to input that into a machine calculator to evaluate it. And so one tool that we have for logarithmic evaluation is the ability to change the base to help with evaluation. And really it's a rule that we call the change of base rule. So we'll give the rule and then we'll use it here for this logarithm, and then we'll look at some more complicated examples. But the change of base rule says something like this. If I have a logarithm to some base b of argument x, that's equivalent to logarithm of another base of my choosing, base a of the original argument x divided by log base a of my old base b. And what this allows us to do is to convert any base logarithm into base 10. So we'll apply it here to our first example. If I've got log base 5 of 25, if I just identify my pieces, my b from the original base is going to be 5. And my x that I see here as my original argument is going to be equivalent to 25. And so those are the parts that I'm going to fit into my change of base expression. And then for the base a, what I'm going to choose here is base 10. And again, that's a convenient choice since calculators traditionally have base 10 logarithms programmed in. So let's make that conversion and then we'll evaluate. So our log base 5 of 25 is equivalent to log base 10 of my original x, which is going to be this 25, all divided by log base 10 of the old base, which was 5. And at that point, once I have the expression recorded, I want to take it over to graphing calculator and just evaluate. In fact, it could just be a scientific calculator. So we will jump over to Desmos and let's calculate our expression. So I'll put the fraction, we'll go log. Now I could put base 10. A lot of times base 10 is just suppressed. It's the only base for logarithms that we could not write it. So we could just write log of 25 divided by log of 5. And right away, Desmos tells us that evaluates as 2. So we'll head back to our notes just to finalize that answer. And really give a quick check. Since this is a simpler logarithmic example, we can check with that answer to see if it's reasonable. So just one thing we can do with the logarithm is convert it to an exponential. So if I have log base 5 of 25 and it equals some value y, I can write this as an exponential 5 to the power of y equals 25. And that would be an equivalent expression, 5 to the power of y equals 25. So really we're asking ourselves here, 5 to what power would equal 25? Well, 5 squared. 5 times 5 equals 25. And that checks out our answer. So we could probably have just calculated this example manually, but change of base works also. Our second example is a little more difficult to see and highlights the use of the change of base rule. Here I've got log base 7 of 343. So if we just think about this again in terms of the associated exponential, just to say what are we really looking for, we're saying 7 to some power should equal 343. Now, the previous example was very simple. I knew 5 times 5 is 25, but I don't know how many factors of 7 I would need to multiply to 343. So this one's a good example for us to use change of base. So again, just to keep change of base rule in view, it says log base b of x equals my choice of base a, log base a of x divided by log base a of b. So we'll apply that here. For my log base 7 of 343, again, I'm going to change it to log base 10, and I could write that, or I don't need to write the base 10, of the original argument 343 divided by log base 10 of my old base, which was 7. So again, I don't really know how many 7s would need to multiply to equal 343. So let's evaluate using Desmos. So just like we calculated for that first example, we will put in log. I can put the 10 or take it off of 343 over log base 10 of 7. And it turns out that I would need 3 7s to multiply to equal 343. Those two examples evaluated as very clean counting number values. So our first example evaluated as 2, the second one evaluated as 3. A lot of times logarithms and bases with their arguments don't evaluate to natural numbers. They are irrational. And so we see here with this last example, even the instructions hint towards the fact that we really need a calculator to evaluate this logarithm base 8 of 9.2. So here, again, just to say what we're trying to find, it's 8 to some power y equals 9.2. So as I think about that y, it's got to be less than 1 because 8 to the, or a little higher than 1, I'm sorry. 8 to the first power would be just 8. But it's not anywhere near 2. 8 squared would be 64. So y is somewhere in between 1 and 2, probably closer to 1. And here's how we could go about finding out. Again, I'm going to use the change of base rule. Log base b of x equals log base a. I get to choose, and we always choose base 10 because it's in the calculator, of the argument. Oops, I'm actually writing the example. The old x over log base a of the old base b. So we'll actually evaluate here. So for log base 8 of 9.2, that's equivalent to log base 10 of 9.2 divided by log base 10 of the old base 8. And I'll use the approximated equal sign because we got to round here to the nearest thousandth. Again, let's take this to Desmos. So we'll set up our fraction log. Here we'll put the base 10 of 9.2 over log base 10 of the old base, which in this case is going to be 8. And as we predicted, it's really close to 1. It's definitely an irrational number. If we're rounding to the nearest thousandth, we want to take it out to 3 places to the right of the decimal. So 1.06, and we'll stay with 7 because the next value is 2 less than 5. 1.067. And again, we could test it out just trying it. 9.8 to the power, or I'm sorry, 8 to the power of 1.067 is very close to 9.2. And we'll record that here. So our final answer here is going to be 1.067. Thank you for joining for this investigation of evaluating logarithmic expressions using the change of base rule. See you soon.